right now, which was something I could not do on Monday because this whole setup is a little bit different. This room used to be functional, used to have a functional setup, and then they found that 306 did not have a functional setup, so they cannibalized the setup of this classroom to 306 and then swapped the non-functional setup to this classroom because no one wanted to teach in this classroom because they were all math professors and they could not deal with whiteboards like that. Yes, go ahead.
I was going to say, what do they teach in that class? And then you answer the question with math
Yep.
professor.
Yep. So we exchanged room 321 for room 308. So CIS, or BCS gets this room, and then math is now getting 321, which is a really good classroom. Big, huge, whiteboard that I do not use, but I do not use a whiteboard, so it's okay to be here as well. All right. So first thing first, did you guys study your Boolean operators? If I ask you what is false implies true, what is the answer? It is true. Very good. Okay, so that is the correct answer. So today, because I got my full setup here, I can now actually make use of my tablet, which allows you guys to see stuff. Yeah, that's just me grading CISP 310. And this allows you, I need to move it around a little bit. Okay, so I'm going to use this as a whiteboard. This is from CISP 310, but I will switch to this class. So give me a second here to go to one more folder up, and then 440 down, create notes. And let me see if this keyboard can type. Oh, great. So I can actually remotely operate my tablet from the keyboard of my PC. So this is going to be 2023, August 23rd. Press the enter key. Oh, it doesn't do it like that. Okay, one more time. All right, so how do I... There we go. All right, excellent. So now we have a whiteboard. Everything that is projected is being recorded. So that means if it's on this, you don't have to take notes, meaning that you'll be in the recording. Now, just because I am doing this doesn't mean that you should not take notes as well, because what I'm doing here is a presentation. So when you look at this and go like, oh, okay, so this is blah, 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 and you make a connection, I cannot record what is on your mind, okay? So you should still continue to take notes, particularly focusing on, what you are thinking about when you see something on being, whatever is being projected. Okay, so the question is, because I verbally describe the problem and then someone answered the question. That's great, but some of us are not as good in terms of just getting the audible or audio information. I'm one of those people, so we'll go ahead and rewrite the whole thing. So the question is asking, what is false implies true? That is the question, and the answer is, it is true. So do we have any questions about this statement? And the statement can be true, can be false. In this case, it is a true statement. Are there any questions about it? No questions about this? If there are no questions about this, I'm not a mind reader. Yes, go ahead.
Well, I'm looking at the truth table that I grabbed, and it says it would be false.
No,
right?
That'd be true implies false.
Well, that's not a... Okay, so you're correct. This is supposed to be true, but I want to find out, where in the truth table might have given you the idea that this is false. So let's go ahead and go to the truth table. So we go to Boolean operators.
That's equivalent.
Okay, so you're looking up the wrong table.
Oh, wrong table. No,
Okay.
Totally, it's true. That's
Yep.
my bad.
So this is implication. So what we are trying to look up, in terms of the question that I posed a little bit, would be the second row. False implies true is true. So we read off the second row of the truth table in this case. All right, so do we have any questions about this? Okay, yep.
Could you just briefly go over NAND?
Say that one more time.
Could you briefly just go over NAND? Because like the one above this one.
The NAND.
Yes,
So the NAND is really, I just threw that in here, as a operator, a Boolean operator, but it's not going to be too useful, not in this class. It is much more useful in CISP 310, and also in, if you are going to become a computer engineer or an electrical engineer, this is of great importance. But if you're just programming, okay, it's not as important, not in this class. But basically, it boils down to x NAND y is really the same thing as the negation of x and y. That's why it's called NAND, because the first and stands for negated, so it's a negated and operator. All right. So, any other questions about this module? When I say module, I'm referring to just one piece of my writing. So, are there any questions about this particular module? No questions? All right. Well, we'll see. Okay. Because implication is an extremely important operator in this class. It. Okay. We'll see. So now we can move on to the following module. So from your perspective, the next module, if you just kind of read down, continue to read, would be basic set theory. So I hope some of you have time to pre-read this particular module. Some people may have taken the class before this one, and they talk about set theory, and some other people may have no exposure to set theory at all. So in this class, we are mostly just talking about notations and not so much on the theorems in set theory. So we are not going to get too deep into proofs of properties of these operators. So here's set theory, and then we just scroll down a little bit. So the first concept that we need to introduce is what is a set and what are elements. A set is a container. Okay. In other words, it's like a folder. Okay, if you look at a file system, a set is a folder. It can contain stuff. So now the question is, what kind of stuff can it contain? Well, just about anything you want to throw at it. Okay, and then the next question is, can a set contain one item and it is also a set by itself? So that translates to, can you have a folder in a folder? What is the answer to that question? Yes. Okay. So they can nest. Okay. So it's, the containment thing can nest. So each thing that is inside a set is called an element. So an element of a set is basically just saying that, oh, this thing is contained in a particular set. So are we okay so far with those two terms? What is a set, which is a container, and an element specific to a set, which is contained in the set? We good so far? Okay. So we'll keep reading. The most basic concept, is the set containing or not containing a particular thing. If it does contain, it is an element. If that thing is not contained in the set, then it is not an element. An element which is contained in a set can be just about anything that can establish uniqueness. So you have to be able to compare two things and say, are these two things the same or not, before that those can be considered as elements in a set. In other words, given two values that may be elements, we need to be able to compare to see if they are the same or not. So the importance of this particular point has to do with, when in this class, when we talk about a set, you cannot have duplicate elements. Okay? A particular value can only appear up to once in a set. Any questions at this point? So right now we understood a few things. We understood a set is a container. Things that are inside a set are called elements of that set. And elements of a set cannot be duplicates of each other. They all have to be unique. Are we good with those three concepts at this point? It's kind of hard to give you, examples, at this point, because when we start to operate things in a set, then we can start to have examples because we're actually doing something. But right now, I'm just explaining the concepts. So there are a few other things that are important about elements in a set, and this is it. Okay, elements in a set are not ordered. Now, this makes a big, huge difference compared to other things that you might have encountered, like an array. An array is a container of sorts. Okay, because you can address elements in an array using the index operator, the square bracket thing. Okay, but there are two major differences between a set versus an array. The first one has to do with uniqueness. Okay, if you have an array of four integers, can I have the same value for all four elements in the array?
Yes.
Yeah, sure. I mean, that's usually how you want to initialize before you do any type of processing or input with an array. But with a set, you cannot. If you have four elements in a set, there are four things in a set, they must be all different from each other. Is that okay? All right. Second thing is what is being highlighted right now is elements in a set are not ordered. There's no intrinsic order to the elements in a set. You cannot say this is the first one, this is the second one, and so on. But elements in a set, I mean in an array, excuse me, elements in an array are ordered. You can refer to those elements as, oh, this is at index 0, this is at index 1, this is at index 2, this is at index 3. So there is a specific order to the items in an array. But when you're talking about a set, there is no intrinsic ordering whatsoever. The only thing we know is whether this thing is in the set or not, but we cannot tell what is the positioning of that thing in the set because there's no intrinsic positioning of items in a set. Are we good so far with those four concepts? Okay, so we are basically just stacking up, the concepts. We now have four concepts related to the concept of a set. The next one is we actually talked about it already. They have to be unique. So somehow I managed to do a little bit of repetition of the topics of the concepts. So the last concept is all elements in the set must be unique. So they cannot be the same. You cannot have duplicates. All right. Are we good so far? Okay. So if we're good at this point, we can start to introduce symbols or syntax or notations, however you want to call that. So right here we have an example. Uppercase T is a set. So we use the braces as delimiters to enumerate what is in a set. In other words, um, open brace basically says, okay, the elements contained in this set starts here. And then you use a comma separated list to show the membership of items in a set. When you're all done, then you use a close brace to say that this is the end of the membership of this particular set. So is that okay so far? All right. So in this example, we have T as a set. Now, how do I know T is a set? Because the way I define T is using the braces. Okay, so the braces is very important. It indicates that we are describing membership of a particular set. So what elements are in this set? The value 12, the value 5, the value 2.2, the value 7, the value -1, and the value 10. So these specific numerical values are members of the set T. Are we good so far? So do I have to list these specific values in this order?
No.
No, because earlier we already said, or there's no intrinsic ordering. So that means I can switch around the ordering as long as I have exactly the same values, inside the brace. It's still describing the same set. Any questions? Okay, yep.
Can elements of a set be of different types? So say
Yeah.
you store numbers and say names or strings.
That is a trick question because it depends on which class you're in. When you're in this class, then the answer is yes. There's no restriction that you have to have the same type when it comes to elements of a set. Because mathematically speaking, a set is nothing more than a container. There is no type limitation. Now, on the other hand, if this is CISP 401, which some of you are taking, then the answer is yes, there is a restriction. If the question is about even C++ in CISP 400, if you're thinking about the template class of set, then the answer is yes, because you have that template in square bracket that limits what type of value can be in the container. But mathematically speaking, there's no such restriction.
Okay.
All right, which makes it possible to make hierarchical sets, which means a set may contain some of its elements being also sets, and then those can also contain some of the other sets. So that's how you can get it into hierarchical in a hierarchical manner. So the next notation that is important is this little symbol here that looks like an E, uppercase E, except it's rounded instead of squarish. Okay, this is the operator that we call element of. Okay, so if I read this example here, it is saying 2.2 is an element of T. It is a statement, which means it can be true, it can also be false. So in the case of how we define T up here, you can see that 2.2 is indeed a member of the set T. So that means this expression, this statement, evaluates to true. In other words, this is not stating that 2.2 is indeed an element of T. It is actually asking, is 2.2 an element of T? So there's a very clear distinction between this is asserting something as opposed to it is asking, is it true or not? I do not know. Okay, so tell me whether it is true or not. So I give you another example that is false. 23 is an element of T is false because according to this definition of T, 23 is not a member. So I'm just going to pause here to make sure that we understand the operator and how we list the membership inside a specific set. Are we okay with those concepts? Okay, looks like we are good to go. All right. So food for thought, which are things that I want you to kind of think about, but it's not crucial to this class. How would you implement the concept of a set in C or C++? If you know ahead of time a set is only to contain integer values, how would you implement a set? How do you check whether a value is an element of a set, and how would you place elements into a set? In other words, you look at a set here and go like, okay, it's initialized to have nothing, but I want this value to be a member of this set here. How do you perform that operation? But there's a reason why we talk about set in a CISP class. This is not a math class. This is a CISP, specifically programming class. So can anyone just imagine why it is important to understand set notations or set operations when you are a computer science person?
To organize.
To organize? Okay, maybe. Yep.
Data management.
Data management. So there are maybe a few cases where uniqueness is needed. For instance, if you are looking at a database, a relational database, the primary key to a table has to be unique. So there it bears some resemblance to what we are talking about here. Okay? Anything else? Yep.
Maybe to know which elements are not in a set.
Say that one more time.
Maybe to know which elements are not in a set.
Maybe, okay, so that's a low level operation. That's the element of operator. But as a computer science person, why do you need to know that?
Maybe determine the range of values you need for a function.
That is a very interesting statement, okay? Because there is a limitation to how many values we can represent given a certain number of bits in an integer. So knowing whether a value is within that set is kind of important, but we can do all that without understanding the concept of what is a set and all the set operations and whatnot. Okay, so anyone else?
I guess a practical reason would be like if you need to associate a user ID with a person's name, you don't want to have a username that correlates to multiple people.
Mm-hmm. Okay, so that's an interesting application of the uniqueness of elements within a set, right? So I'm going to look up some algorithms. Specifically, I'm going to look up Dijkstra's algorithm because this is one of the algorithms that we'll study close to the end of the semester. So we go to Wikipedia and we want to find out how this particular algorithm is expressed. So we get to pseudocode, skip all the way, and all right. So right here we see one of the operators that we talked about, even though it is not exactly using the symbol. So in is asking is a vertex in Q. And what exactly is Q? Q is a set. So I think this gives you some idea of why it is important to understand set as a notation, the operators and whatnot, because complicated algorithms often make use of set operations to express the algorithm itself.
So
Mhm.
looking for pathways and it's separating the ones it's already been through.
It looks for the shortest path.
Yes.
So Dijkstra's algorithm is the first algorithm to find the shortest path between 2 points in a graph. So if you think about Google Map, okay, you're trying to go from a specific place to another specific place. Dijkstra's algorithm is one algorithm that can help solve the problem. And this algorithm was derived in the 50s, and at the time, this was considered artificial intelligence or machine intelligence.
That is a
Because before this, there were nothing, okay, that can help you find the shortest path. And at the time, people thought only people can solve this problem. The computer is only good at computing, like figuring out the numerical value of sine, cosine, and stuff like that. So this was once considered artificial intelligence. Today, we look at this and go like, yeah, that's a topic that we'll cover in 2 weeks in CISP 440. And this is a lower division class at a 4-year university, so it's definitely not considered AI anymore. Okay, but it still helps to illustrate why we need to understand set notation because algorithms can be expressed using set operations as primitives. Any questions so far? No questions? Okay. So if set, okay, go ahead.
what does the backward arrow mean?
Hmm?
The backward arrow?
Oh, this arrow here,
Yeah.
that's your assignment operator.
So you
It's the same as a single equal in C and C++.
okay.
Okay, but that's a good question. Why don't they just use a single equal like everybody else? Why use a left arrow to represent assignment operation?
Show that value is moving into that.
Mhm.
Into that.
The equal symbol is very ambiguous, okay? Because you can say, am I stating the left-hand side and the right-hand side are the same? Am I asking whether they are the same? Or am I copying whatever is on the left-hand side, right-hand side to the left-hand side? Okay? How many people have made that mistake? That you're supposed to be using equal equal in your program, and then you just use a single equal. Is that syntactically correct? Most of the time it is, okay? As long as the left-hand side is a variable, it is syntactically correct. You can embed an assignment operation in an expression in C and C++. But if that is not what you intend to do, then the end result can be a little bit disastrous because you would actually change the value of a variable that you only intended to compare to something else. Okay? And that's why when people specify algorithms, you know, you know, computer science people are different from developers in the sense that computer science people do not actually quote unquote write the code, they specify the logic. There's a difference between coding and just the logic, because if you just want to specify the logic, it's pseudocode. As long as somebody can understand this, we are good. But a developer needs to write code that is understood by the computer. So you have to understand all the syntax, use the correct syntax, and so on and so forth. So there's a major difference between those two different types of occupations. Both are related to computer science, but the nature of the job would be different. But anyway, this is just an example of why we need to understand set notations. All right, section 3, it talks about how do we know two sets are actually the same, okay? So a set can be compared to another set to see whether they are the same or not. But you cannot say one set is bigger than the other one, okay? You cannot say one is smaller than the other one, okay? So later on we'll talk about cardinality, then you can say, does this set has more elements than the other set? Sometimes you can do that. And some other times, you cannot even do anything like that. And we'll get into those really kind of weird cases later on in this semester. So at this point, we lack the precise mathematical notation for this kind of discussion, but we can still utilize English for the most part. Let's say we are interested in whether set S and T are the same. The two sets are considered the same when every element in S can also be found in T, and every element in T is also found in S. Does that make sense to you? Okay, all right. So if this requirement is satisfied, then we say the two sets are actually the same. All right. Any questions up to this point? Because these are fairly abstract kind of discussions, so I do want to double check and make sure that we get all the concepts before we move on to the next one. Yep.
Would you say, like, because they're the exact same, would you say T is an element of S and D? No, you wouldn't say that at all.
Nope, I would not say that. It's kind of like asking whether this folder has exactly the same content as another folder. So what constitutes equality when you're talking about folders? So you're talking about a folder that is on your usual document subfolder and a folder that is on your backup drive. Okay? So you're asking and say, hey, if they're already the same, I don't need to do any copying because my backup is up to date. So the question is, what determines that these two folders are the same? You must have the same files, right? But what if you have folders of folders, okay, and then folders of folders of folders of folders and so on? That hierarchy has to be preserved in order for this folder to be considered the same as the other folder. Same thing with set operations. So for the most part, when we think about a set as a folder, and individual elements that are not a set as just individual elements, it works. Okay, that analogy will take you a long way. Yep.
So did you say earlier that when comparing two sets that you can't say that one set is larger or smaller than the other?
There's no such thing in mathematical definition that can say one set is larger than the other one. Now, once we get to cardinality, you can look at the number of elements of one and compare that to the number of elements of the other one. But it's not whether the set is larger, it's whether the number of elements is greater than the number of elements of the other one.
Okay.
So you can compare that once we introduce cardinality, which is really just counting the number of elements in a set. Professor, I got a question. What about the set of all the integers versus the set of all the real numbers? They both have an infinite number of elements. And how do we compare? What about the set of all natural numbers versus the set of all integers? Now that one is interesting. So we'll get to that one and say, okay, so how do these compare? As it turns out, they have the same cardinality. You go like, how can they have the same cardinality? It doesn't make sense on multiple levels. One is there are things in the set of integers that are missing entirely in the set of natural numbers, like -1, because negative one is an integer, but it's not a natural number. So you go like, so if there are things missing on one side and everything on that side has to be on this side, surely we can say that set has more elements than this set here. The answer is no, you cannot say that. Because they both have an infinite number of elements, and infinity is not greater than or less than infinity. There's no way you can compare infinity to infinity. You go like, okay, so how do we know they are quote unquote the same? So we'll get to that after we talk about functions, because there's a very, very specific and interesting way to say, oh, by the way, these two have the same cardinality, but they're not even countable. Okay, I take it back. The number of elements is infinite, but they have to have certain properties so that we can say, yeah, they have the same cardinality. So we'll get to that. It's called Aleph Null. There's one entire module dedicated to the discussion of just Aleph Null. All right, so we are moving on to section 4, which is, can we have a set as an element of another set? The answer is, yeah, sure, why not? You can have a folder as a component of another folder, right? Same concept. There's no real, conceptual difference between those two and those two. So we'll take a look at the text here. We call that, to qualify as a potential element, a value must be comparable to other values to determine whether they are the same or not. In the previous section, we just established that a set can be compared to another set to see if they are the same. So that means, I can have a particular element in a set that is by itself also a set. So in general, if you are given two values, x and y, knowing that x is a set, this is how we can determine whether x and y are the same or not. If y is not a set, then we don't even bother because we have a type mismatch problem. If they are both sets, then we use the set comparison method in section 3, which means, oh, for every element on this side, can I find it on the other side? And for every element on the other side, can I also find it on this side over here? It has to go in both directions. Now that we can compare a set with anything for equality, it is not surprising that a set can be an element of another set. For example, x in this case is a set because it starts with a brace, it ends with a brace. But when you look at the elements that we have enumerated, it has element A, it has element B, and then it has an element that by itself is also a set which has elements, which has values 1, 2, and 3 in that particular set. That's perfectly okay, not a problem. Okay. So now when we ask, when we are presented this particular expression, is the set that contains 1, 2, 3 an element of x, then the answer is true. It is. All right, so I'm going to pause here and see if there are any questions.
So if you have a set within a set, can that set that is nesting, can it have the same values as the values in the original set?
It cannot, right? Because it doesn't make sense. Because in order for a set to contain itself, now you have an issue, because then it's never defined. You can never really fully define the membership of a set where it is its own element. It's just like a folder cannot contain itself. It's the same issue.
Would it be impossible to write
Hmm?
a set, like the set that he described? Would it be impossible to write, or would it be possible to write?
To write,
So that's
as a notation.
Yeah, as a notation.
There is a specific branch of math where they do allow that type of membership.
Sure.
So it's a whole different branch because it leads to all kinds of things that we do not encounter in this class.
Uh-huh.
And there's also the concept of a multi-set, where a set can contain duplicate elements, but that is not what we are going to talk about in this course, because I need to prepare you guys so that you can understand algorithms that use set operations as primitives. That would be one of the objectives of this class. Because when you move on to a 4-year university, there should be at least one class called the analysis of algorithms. And that's all they talk about. Okay, they present an algorithm, maybe something that you already know, like bubble sort. So what are they going to talk about? In bubble sort, it's not even a programming class. They're not asking you to write a program to implement bubble sort. They'll be asking you to mathematically prove that bubble sort is a correct algorithm for sorting. It's a mathematical proof, which means you're not just going to say, okay, if this is the input and that's the output, hey, that shows that the algorithm is doing its job. That is not a mathematical proof. It has to be a mathematical proof in that class. They will ask whether the algorithm is going to terminate or not. In other words, given the problem is solvable, is the algorithm going to conclude at some point in time or not? I mean, it seems to be pretty clear that, yeah, the algorithm should finish. No, it's not. It doesn't have to. Okay? So those classes will rely on the vocabulary that we are building up in this class. In other words, we are learning the ABCs relative to that class that you will take at a 4-year university as an upper division class. You guys do not seem too excited. Yes, this is great. I love this stuff. Yep.
Let's say we have another y set and it's a a, b, 1, 2, 3 as an element. Does x and y considered to be equal?
Okay, say that one more time.
So if we have another set which is y
Mm-hmm.
and has an element a, b, 1, 2, 3 in a single set,
Yeah.
without a set inside set, does the x and y equal?
All right, so let me give you a few examples, and you guys tell me whether the two are the same or not. Okay, because I think this is a great way to kind of check in and see if we are really getting the ideas or not. So I gotta do one thing first. There we go. All right, so I can do this using just a text editor because I can type a whole lot faster than I can. Oh, yep. Okay. Always stick a pen into that. All right, so I am going to show you a few examples, and we'll talk about why, we'll talk about what the answer is, and then for the tricky ones, we'll talk about why the answer is the answer. So we get the mouse pad. There we go. All right. So the first one is that. Are these two the same? They are the same. You have two empty folders. So if you ask me, is this empty folder the same thing as the other empty folder? The answer is yes, because they both do not contain anything. Okay. So now we move on to something that's a little bit more. Okay, what about this?
Yes.
They are the same, but one is AB and the other one is BA.
Doesn't matter.
There's no ordering, right? There's no intrinsic ordering to elements in the set. Very good. So now we move on to something that is nested, like this one. And I'm asking whether it is the same as. Okay, what about this?
No.
Very good. Okay, they are not the same. Why not? I mean, it looks like A, B, C are both, and they're all in one and also the other one. But, yes.
Because the first set contains the set B. The first set contains a set that contains BC in it, while the second one is a set that contains a set that contains AC in it.
And they are not considered the same.
Yes.
The set of BC is not considered the same as the set of AC, which means there's an element of the set on the left-hand side that is not on the right-hand side. Done. Okay? The other way to look at this is the set on the left-hand side has an element of A, but the set on the right-hand side does not have an element of A. Even if it looks like A is in there, it is not an element of the overall set. It is the element of a element of the overall set. Yep.
How do you check the nested set?
Hmm?
How would you check the nested set?
Well, remember how we established equality? So the way to do it is to say, okay, this is an element. Is it found on the other side? So what elements are we looking at on the other side? First of all, how many elements are on the right-hand side? If you just look at the overall set, there are only two elements. This is one element of the set, and this is the other element of the other set.
Yes.
So when you look at the value of A, it does not match B. It also does not match AC as a set. That's the most important part. Is even though the letters are all here, they are arranged or structurally they are not in the same type of containment hierarchy. It's just like you have you have three files, okay, and then you have the folder structure, arranged like this, and you're asking, is this folder structure the same as the other folder structure? And for anyone who says, yeah, they have the same file, well, I'll give you this example. Let's say you have 10,000 photographs, okay, digital pictures and whatnot, and you like to arrange everything by year, and then by month, and then by date, okay? And then your buddy goes like, that is just wrong. Okay, this is the wrong way of arranging things. I like to arrange things by which trip we are on, and so on and so forth. So you give your folder that contains the 10,000 pictures with year, month, day as subfolders to your buddy, and your buddy goes like, I'm going to rearrange things. Okay, and your buddy gives the folder back to you on the thumb drive, and you go like, I cannot find my stuff anymore. What did you do to my folder? That's why they're not the same. So is that better? Is that a better way to kind of describe this? Because you cannot find the stuff anymore. It is not in the same hierarchy anymore. All right. So I think that's enough to illustrate all the concepts that we have talked about. And I'm going to have to emphasize this is false. It is not true that those two sets are the same. Whereas before this is true, and so is this. Yep.
So for the third one, do you read it as like A is element 1 and then element 2 is BC?
Yes. Yep. So when you look at the left-hand side of the equality, it is a set, and it has two elements. The first element is just A, and then the second element is B, C in a set. Mm-hmm. All right. So now we are concerned about how do we describe, okay, not let alone operate on, but we are just trying to describe sets with an infinite number of elements. Okay, what do you mean by that? Well, let's think about, we want to think about a set of all even numbers or even integers. Okay, there we go. I mean, it kind of implies that an even number is an integer, but I just make it extra, explicit. All right, so how would this describe that? Well, there are a few ways, right? One way is to list by example. So listing by example is something like this. The set E has a bunch of elements. Dot, dot, dot means, there will probably be stuff before this. As examples, we have -4, -2, 0, 2, 4, and then a whole bunch of stuff after that. So, this is a first attempt, okay, to tell somebody else that E is a set of even numbers. Well, but we really do not know what the dot, dot, dots are representing, right? For all we know, it can be -6, -8, -10, -12. They're all so that those are the even numbers. But it can be something else too. So this is not a very precise way of describing a set of even numbers. Why do we care about precision? Because we're dealing with computers, and mathematics is also a language that has to be precise. But why is math important to begin with? Why do we have to learn math when all I want to do is to write some games? Why am I stuck in this class?
Because algorithms are arithmetics.
Yeah, the mathematics. Okay. Um, there was another hand up. Go ahead. I think there was a person over there. Nope. Okay. Yeah, because math is really important. Um, we'll get back to that a little bit later too. Okay, there will be multiple occasions that I will go back and explain why it is important, why the fundamental stuff of math is really important. All right, so moving on. So the following notation can be used as a precise and also concise method to describe a set of even numbers. So this is one. Okay, so we'll take a look at this notation here. E is a set where where each element x has to be in the set of integers and x mod 2 equals to 0. That is how it is read. Let me say that one more time. And if you think I'm not going to take notes, but I might want to get back to this moment, what do? You look at the time and you jot down the time and the date. Okay, so that's kind of the minimal note taking that I want people to do. Okay, so I will say that one more time. So E is a set where each element x has to be found in Z, which is a symbol to represent the set of all integers, and x mod 2 equals to 0. We good so far?
Yeah.
All right. Well, x is an element of Z may not be required because if x mod 2 equals to 0, x has to be an integer. Okay, so for the most part, 1 is not needed. Okay, I got a few questions, that I want to ask. You don't have to answer. Okay. I want to make sure that we all understand this means logical AND. Now, if for some people you're saying I have no idea what that is, that means the content of the Monday lecture was not reviewed, and it is crucial to review the content of a previous lecture because I am infamous for stacking up things really fast. So I would rely on content that has been previously introduced in just a lecture before and use it right away. It's like, yep, I'm going to use it right away here as a definition. So that's one thing. And two, in case somebody says, well, I know where to find the definition, that's not a bad answer, okay? So we cannot remember all the details all the time. I know you take some other classes too, and there's only so much you can, cram in your head. So that's okay if you cannot remember exactly. But if your answer is, oh, I have the definition in my own notes. It's right here. All the definitions go here. I go like, okay, that's good too, because you have a place to find it. On the other hand, okay, if you say, I know you talked about it on Monday, I know which module on Canvas to look to find it, it's like, yeah, that's an okay answer, but at least you know it is in the notes and you kind of know where to find given enough time. For people who say, I have absolutely no idea what it is and I don't know where to find the definition of that thing, I worry. Okay? So I just want to make that clear, okay? Because in order to proceed in this class in a successful way, you really want to get all the definitions, as soon as you can, and make sure that you have a way to help you remember the definitions, okay? The symbols, definitions, and operators, and so on. Okay. Are there any questions about this notation?
So at the very beginning where it has the X and then the pipe, what does the pipe mean?
The pipe literally says such that. So the whole thing is basically saying E is a set because it is indicated by the brace such where, okay, so there's a word where that is not appearing anywhere here as a symbol. So it says where each element X. So this is the format of an element in the set such that that element X has to be also an element of Z and X mod 2 has to be 0.
And this just basically means, like, X is just kind of an example variable, but it means every element of E.
Right. It's a placeholder and say if there are elements in this particular set, each element that is an element of this set, we'll call it X, and for that particular X, it has to meet these requirements. So it is a way to describe the criterion or the criteria to be qualified as a member.
So it's pretty much like when you declare like int I like a for loop or something.
A little bit more than that. Okay, it's a little bit more than that. The next few paragraphs would also help to clarify this particular notation. All right. But but there are more to this. Okay, because the sentence that I used, the phrases that I chose are very specific. This notation literally says something X is an element of set E, and I chose to use if and only if, and not just if. Not only if, but it is if and only if X is an element of the set of integers, which is what this expression is saying, and X divided by 2 has a remainder of 0, which means X mod 2 is a 0. So the phrase that I chose to use, if and only if, is important because it says if something meets this requirement, it has to be a member of E. But it also says the opposite, which is basically saying if I just pick something out of this set here, it also has to meet that requirement. It goes in both directions. Does everybody understand the importance, the significance of using if and only if to limit the membership? Okay, all right. So moving on to the generalized notation. So in general, if we consider P of X as a general predicate P on X as a function that returns true or false based on X, then blah, blah, blah means exactly the same as blah, blah, blah. All right, so we'll explain the blah, blah, blah later because the first thing is what exactly is a predicate? We never really talked about what a predicate is. Well, from your perspective, because you have taken CISP 360, 400, and 430 up to this point, so a predicate is nothing more than just a function that returns a Boolean. That's all it is. Okay? It's a function that returns a Boolean, which means it only tells you whether something is true or false. And in this case, this particular predicate takes a parameter x. That's basically what it is. So P of x is basically using x, which is a value, and it will just return true or false. Okay, so any function that returns true or false? Yes, any function that returns true or false, given a particular value. Okay, so the notation, because we are focusing on the notation itself, so we are not too concerned about true about what? I mean, what about x being true and what about x being false? We don't care, okay? It's just a function. What we do care is the notation. E equals to a set where each element x has to evaluate P of x to true. Okay, that's basically what this is saying. But that really means exactly the same as the following one, where you have a hidden parentheses on between x is an element of E, and before so there's a close parenthesis before the if and only if. Okay, so the second form is saying x is an element of E if and only if P of x. What do you mean by that? if and only if P of X. Well, implicitly it is saying if and only if P of X is true. Okay? So the whole sentence to describe the second form is saying X is an element of E if and only if P of X returns true. So I'm going to pause a little bit, see if it sinks in, so that you can say, okay, I can kind of see how it's really just a formatting thing, but these two are really defining E exactly the same way. Are we convinced? Because if you're not convinced, and then you can present an example of what about this? Okay, P of X is like this, and E is like this, and it does not seem to match the description here. Do we have any questions here? Because we're going to use this notation quite a bit. So we really have to make sure that we do not have any questions about the notations or the operator if and only if.
Why would you use one notation over the other?
Say again?
Why would you use one notation over the other?
One is easier to write. It's more conventional that mathematicians would tend to use this notation here. This notation means the same thing, but it doesn't mean that we use it as often.
So the top one's more common.
The top one is more common, just as a convention. Now, convention is unfortunately also important when it comes to mathematical symbols and programming and whatnot. I'll give you one example. For those of you who took C++, what is this in C++ or regular C? I mean, this is an operator that you should know already by now.
Accessing a member of a
pointer.
Accessing a member of a pointer.
Yes. So the long way of this, the correct way to describe this is we are accessing member M of the structure that pointer P is pointing to. It's a mouthful, okay? But this is really exactly the same as dereferencing P first, then use the usual dot notation to designate the member. But the right-hand side is seldom used, even though it means exactly the same thing as the left-hand side. So it's a convention thing. Okay, so likewise, okay, in our notes here, this is usually how people describe membership of a set, even though this means exactly the same thing. Are we good so far? Okay. All right, so let us generalize this to the following example. X is the set where element E, such that when E is a member of X, as long as E can make P of E true. In this notation, P of E is called a predicate on E. It is some kind of Boolean expression, so we talked about this already. Given that P is a predicate, this notation says exactly the same as the following. Okay. All right. Any questions at this point? So I can generate a few questions, like I give you a particular description like this, and then I can ask you, how about this thing here? Is it a member of that particular set? And then you should be able to evaluate and find out, yeah, that thing should be a member. Oh, not this thing here. This thing is not a member of that set. All right, so I think I'm about to take roll today because I completely forgot on the other day. So the way we take roll is for you to sign in to Canvas. So take your mobile device out or your cell phone or your laptop or Chromebook and sign in first. And I have this activity here. I'm going to move it up here. All right, so you cannot see it yet, okay? It is still hidden at this point. So I'm going to point out how you do this. So I'm just going to add a little bit more description here. There is an access code. So the access code in this case is just lowercase yay, Y-A-Y. Okay, so write that down on a piece of paper or just remember. And then the question that you'll be presented once you get into the quiz is whether you're in class today or not. It is also a Boolean type of answer, true or false. So knowing all that, I'm gonna save and publish, which means now you should be able to access it. So people who answer true, yes, I'm in class today, will have a positive attendance record. People who are not even here and only watch this from the video later on will have a 0 or negative attendance. And people who answer false will have 2 absences recorded.
You did this last semester too.
Yes.
Did you post it?
Hmm?
Did you post it?
Oh, I posted, but I did not specify the time. I think that may be the reason why you guys cannot see it. Okay. Huh?
It's in the modules.
Oh, it's in the modules.
Yeah.
Yep.
It's in the set theory module.
Yep, I'm gonna put a deadline here. It's 4 o'clock. Do you think 10 minutes is enough time? So I'll give you guys up to 4:10 to respond to this activity. And for those of you who have no mobile device, and you can just write your name or and your student ID on a piece of paper, and then just leave it with me, and I'll enter your attendance for you. All right, cool. Question? Yep.
Can I ask a question about the basic set theory?
Mm-hmm.
So when you generalize the x equal element of E such that P of E, and at the end you say this notation says the following, why is it not PE and but be PX?
So the variable doesn't have to have the same name because it's just a placeholder.
Okay, so this can be whatever.
So whatever symbol you use here has to be the same symbol that you use here. This is mostly because we haven't really talked about quantifiers yet. So once we talk about quantifiers, it will start to make more sense. Because there's an implicit for all in front of everything, in front of what I'm pointing out right here. But we haven't talked about quantifiers yet. So it is just kind of implicit that we have in quantifier. All right, moving on to section 6. A set with no elements. A set with no elements is called an empty set. While there are many representations of an empty set, one is it looks like a 0. It's a circle with a strike through. In this class, I'll just make it very clear and just use open and close braces with nothing in between. That would be our representation of an empty set. So are we ready to move on to set operators? Now, when we talk about a set operator, it means the returning value is also a set. Membership is not a set operator because you have a value on one side, you have a set on the other side, but the answer is Boolean. It's either yes, this thing is an element of the set, or it is not an element. So when we talk about set operators, it means the operator, the return type of the operator itself is also a set. Okay, it produces a set. So we'll start with the intersection operator. This is the intersection operator, and this is how I describe it. Do you see how I'm just instantly reusing something that I just introduced earlier in class? Now, I think it's a good thing because this gives us a chance to kind of practice, how to read this stuff here. It is also a more concrete example, so we can actually go like, oh, okay, so that's how we make use of that notation and also understand what is an intersection at the same time. If you ever wonder, okay, in your math class, you go like, but I want to be able to use all these cool symbols in my math homework assignments and turn in my math homework assignments with all of these symbols. You can, I think I'm pretty sure I talked about this last time, right click, show math as, and then go to the tech commands. It is not text, it is tech, because the X is actually chi as a Greek letter, so it is not X, which is an English character. But that's how you enter it. If you want to put this into your own notes or whatever, just copy to clipboard, paste on the other side, and then you have the math equation. In previous semesters, I would even illustrate using Markdown. So I use, there are many note-taking apps where you can type in this format, and then it will basically give you the actual rendering of the equation. So some people may want to take notes using a computer because you can type faster than you can write. All right, so getting back to the main topic here. What is A intersecting with B? The intersection of A and B is a set where each element E is an element where element E is an element such that E is a member of A and E is a member of B. Yep.
So, what is the difference between doing this and earlier we discussed that A and B are equal?
This one is giving us a new set. So the intersection between A and B can be the same as A, can be the same as B, but it can also be something other than it's not A nor B. So I'll give you a few examples. Okay, so we'll get on to some examples. But remember earlier we also have an alternate representation. So this is basically saying E is an element of the intersection of A and B if and only if E is found in A and E is found in B. All right. So are we doing okay so far with the general understanding of the concept? Okay. Okay. So I see some nodding and some turning head. I'll use some examples. Yes. Go ahead.
So doing A intersection B will basically return a new set that contains elements that are found in both A and B.
That is correct.
Oh, so it's basically merging these two?
That is a very ambiguous word because when you say merge, there are two ways or a few other ways to merge. Because you can say, oh, I'm merging. So if it's in either one, it will be in the final one. Okay. Or you can say, if it's in both, then it will be in the final one. Or you can say, if it's in this one, but not in this one, it will be in the final way. So all of those can be seen as quote unquote merging. So this one is much more specific. So I'll use some examples to illustrate. So we'll just say one is ABC, and then this is called a cap operator. So I cannot use the actual operator in the text editor. So I'm just going to say \cap to represent the actual operator here because that's actually what it is, when you need to type it in using LaTeX. So, and then we have, BCD over here, okay? So what is the result of this operation? What is the value of the operator?
BC.
Yep, it's just BC. Because B can be found on the left-hand side, B can also be found on the right-hand side, and therefore it is a part of the intersection. And same thing goes for C. What about A? Well, A can only be found on the left-hand side, but it's not found on the right-hand side. Same thing, similar for D, because D can only be found on the right-hand side, but not on the left-hand side. So they do not belong to the intersection. Yes?
What if A and B are the same set?
Well, then you process it exactly the same way. You ask the same questions. You just come up with the answer, in the same way, but it will not be the same. So you have this. Okay, let's make this a little bit more, slightly more interesting. Okay. So what is the answer?
CB or CAB.
CAB, ACB, BAC,
Ooh, I don't like
ACB,
BAC.
and so on.
YMCA.
Why? There's no Y.
MCA.
There's no M either. So A is on the left hand side, A is also on the right hand side. So it belongs to the answer. Okay, so A is an element of the intersection. So now if I need to describe the intersection, then A has to be a part of it. Then I look at B, or I can look at C. I can jump around. C is a member of the left hand side. C is a member of the right hand side. So it is a part of the intersection. Then finally, we look at B, and B is on the left hand side. It is on the right hand side as well. So it should be a member of the intersection as well. Okay. Okay, let's take a look at something else. Let's look at this one, AB intersecting with CD. What would that be?
An empty set.
It's nothing. Because there is nothing that can be found on both the left-hand side and the right-hand side. But it still gives you a valid answer, which is just the empty set, to basically say there's nothing that can be found on both the left-hand side and the right-hand side. Are we doing better now with this concept? Okay, very good. So this is how you study. Okay, so when you are studying with this, it's good to study with somebody else, and then what you're going to do is to present examples to yourself. It's like, what about this one? Let's figure this out. Okay, I got this. I got this. Oh, okay, we are agreeing, and there seems to be no confusion of which one is the right answer. Great. But if you disagree, then you go like, okay, we need to talk about this. Okay, what is the definition of intersection? Okay, you always go back to the definition and then evaluate based on the definition. So that means if I were you, I would definitely write this down on the list of all the definitions and make sure that you mention this is how intersection is defined. Now, for those of you who are more visually oriented, you can also use a graphical way to represent it. Um, the graphical way is good in a way, but bad in a way. Okay, so if this circle is set A and this circle is set B, then this portion here is A intersection with B, or the intersection between A and B. This is called a Vern's diagram, and some people like it, because it's intuitive, but you can really only use a graphical representation up to a certain point. Because what if A has an infinite number of elements and B also has an infinite number of elements? Then go like, how do we draw an infinitely large, thing and describe the intersection? It's like, ugh.
You grab an infinity sign and you merge it with the infinity sign.
So that becomes a little harder, right? So if you want to use Vern's diagram to get a intuitive understanding, that's good. But I would still go back to the definition, to get to the core of the definition. All right, so we are moving on to union. So union naturally looks like a U, okay? So this is union. And when you look at the definition between the differences between intersection and union, they're only off by one little symbol. This symbol here, which is called a wedge, is replaced by this symbol here, which is called a V. It's like, oh, so they're about the same. No, they're not about the same, because this is OR. So in the union, a value belongs to the union if and only if it can be found on one or the other side. Now, this is just a regular OR, it is not either or. In other words, if it can be found on both sides of the operator, no, not a problem. Great. Are we doing okay so far with this? Okay. So we'll go back and revisit the examples that we have already talked about. This is called a cup. Okay, \cup will give you the U symbol when you're using LaTeX. So we'll go back to our example thing here. And as lazy as I am, I'm just going to copy and paste. But this time I change all the cap to cup. So these are union operators now. And then we'll try to figure out the answers. All right, so we'll erase the answers from before, and then we'll work on these. All right, so we'll start with the first one. Okay, what can be found on at least one side of the union operator?
A,
Mm-hmm.
B, C, D.
Yep, there we go. Aren't we missing one occurrence of B and one more occurrence of C?
No, because sets are unique.
Exactly. Okay. So this is the answer should not be two B's and two C's, because elements in a set, they have to be unique. Okay. Very good. What about the next one? What is the union between ABC and BAC?
There is no EC.
It's the same thing as either the left hand side or the right hand side because they are the same. So you can say this is a CB. Okay. Do we have any questions about this one? Okay. And what about the last one here where we got an empty set?
ACBA.
Okay, BDAC. I'm just randomizing the ordering because it really doesn't matter. Okay, I want to emphasize there's no intrinsic ordering of elements in a set. Are we okay so far with all of these examples? Yes.
What is the other way to write A union B? Is there only one way to write it?
A union B?
Yeah.
Okay. Well, that's why we have the cup. Because if you look at the notation that I actually used to produce this output, oh, yeah, I have to do it like this. That's why I use the cup. Because backslash cup defines this operator, the union operator.
No, I mean like for A intersection B, there's two ways to write it. Like for E such that E
Okay.
and then the
All right. So,
yeah.
so if you want something that looks like this, what do you think it's going to look like?
That was B.
B.
Exactly. You are changing the conjunction into a disjunction. Because what you have here is exactly the same thing as what you have here. So if in intersection we are using the conjunction and in union we are using the disjunction, then the other format is going to be about the same, except you change the wedge into the V. All right. So now we have another one. This is less common, but it is still a useful operator. It's called difference. So A quote unquote minus B is a set where each element E has to meet the requirement of E is found in A. And what is this? Negation. And it is not the case that E is found in B, or otherwise you can say E is not in B. Okay? So let's go back to our examples and try to use the minus or this difference operator on all of these and see if we can come up with the answers. Yeah, we have a few minutes. We got enough time. Okay, so this becomes minus, this becomes minus, and this becomes minus. And then the answers are erased because they're all different from what they were for the other operators. Okay. So now let's go from the first one. So we are looking for a set where each value in this particular set can only be found on the left-hand side, but not the right-hand side of the minus. So what would this be? It's just A by itself, okay? Because A is the only value found on the left-hand side, but not the right-hand side. What about this one here? It's an empty set because there is no value that exists only in on the left hand side but not on the right hand side. They're identical. What about this one? It will be the entire set AB because these two sets do not intersect at all. All right.
Why is the word intersect used?
Huh?
Why is the word intersect used when like describing that?
For the cap.
No, I mean in terms of like, is that just like the term that's used, or is there a reason why it's?
Like, why is it called intersection?
Yes.
When we define intersection, or when I refer to intersection, when I said since there's no intersection between these two sets, the entire left hand side is the answer.
The second.
The second one?
Yeah.
Because if the intersection is an empty set, then there are no elements in common between the left hand side and the right hand side. So now, naturally, the entire left-hand side is the answer.
Okay. Yeah, I think my mind's just like going to like graphs and points. It's like
Mhm. Well, we're also close to the end of the 80-minute lecture, and for some of us who were used to asynchronous online classes where you can take a break every 10 minutes, when your attention span now has to lengthen all the way to 80 minutes. It takes some time to get used to it. So are we good so far on all of these operator stuff? Okay. So a few things to do. I know it's the weekend. I know it's strange to say have a nice weekend, but have a nice weekend.
Yes.
But on top of having a nice weekend, review all the stuff that we have talked about, especially when you are when you're listening to me and go like, I kind of get this, but only kind of. That means you have to go ahead and review the material. If you run into problems and go like, okay, I have absolutely no idea how to approach this, come to my office hours. Okay, it is on the syllabus. If you clear all of this stuff here, you go like, I'm all good here. Read ahead of me. Okay, read ahead by about one link would be good, because that means by the time we get to the new material, you go like, yeah, I kind of have some idea what you're talking about. I just need to kind of focus on the details at this point. So that is what you need to do. We don't have any homework assignments, but studying, taking a class is not about homework that I give you. It is about the homework assignments that you give yourself. So give yourself some homework assignments and give yourself a pat on the back. I'll see you guys on Monday. Yes, go ahead.
I do have a question. Will this class just only be exams or will it be assignments? No.
There'll be assignments. So once we are done with all of the set concepts, then I'll give you an assignment. You have a week to do it. Then it's basically a way for you to review and make sure that you understand all of those concepts. But for now, you can use the approach that I did in class. Give yourself examples to work on. So you go like, okay, what is the intersection between these two? What is the union between these two? What is the difference between these two? Is this thing a member of that one? Now, if it is clear that you can get it, great. Work with somebody else too, so that the other person can kind of work with you. And if you go like, okay, I really have no idea what is the answer to this question, come to my office hour because I can then help you talk about those things.
Thank you.
Mhm.
So no weekly assignments.
I don't do weekly assignments because it means more work for me.
Okay.
No, because I think it's important to give yourself these exercises. So when I claim something, oh, by the way, this is just the same thing as that one. Is it really?
Tech
So
said
you,
so.
hmm?
I said yes, Tech said so.
Yes. So you basically have to doubt everything. Okay, pretend that I'm trying to lie to you and trick you for 80 minutes. And go like, how do I know this? How do I double check this? Okay, because these are common concepts in mathematics. So Wikipedia has plenty of material, um, but for the most part, there's not a whole lot that I can ask you at this point. So until we are done with all the definitions, then you get an assignment where you have to work out. Is that the case? What about this one?
That's good.
Okay.
Yeah. Thank you.
It doesn't mean there's no work. It just means that there's no technical homework assignments.
Hey, Tom. When should I ask you again about a waitlist? Like next week?
Again?
When should I ask you about the waitlist?
Well, I just told